Good morning. It's my great pleasure to introduce Professor Chris Brown from Worcester Polytechnic Institute. His talk today is about axiomatic design, which was created by Nam Su, and he'll give you a variety of examples through the whole lecture, and you will see how it can be used in your classroom or industrial setting, as he has done a lot of industrial consultancy and participate in design. So as he says, one of his students introduced him to Nam Su, who introduced him to axiomatic design before 1980, before he came to WPI in 89. Since then, he has worked on product and process development at Atlas Copco, European Research Center. Before that, he studied metallurgy, surface metrology, ski equipment, the materials and mechanical engineering departments at EPFL, the Swiss Federal Institute of Technology. At WPI, he started the surface metrology lab, has technical center for CNC machining and sports engineering lab. So he has developed several courses, two of them graduate courses in axiomatic design of manufacturing process and surface metrology, and undergraduate courses in manufacturing engineering and on the technology of alpine skiing. You know, I'm very far away from alpine skiing. I also do research, publish, lecture, and consult for industry on axiomatic design, surface metrology, sports engineering. He has lots of patents on sports equipment and surface metrology. With that, I will hand over the mic to Chris. It's a pleasure welcoming you.
Well, thank you much. Thank you very much. It's a pleasure. It's an honor to be here. It was actually my professor, Branimir von Turkovich, who introduced me to Nam Su back in about 1980. And that's when I first heard about axiomatic design. So it's ever since I learned about it, I have been using it and applying it, and I found it to be the best way of understanding and creating designs. So, all right, a scientific approach. So I'm at WPI. I have been since 1989 now, and WPI is the third oldest engineering school in the United States. It comes after RPI and MIT. We're about 70 kilometers west of Boston. We got about 6,000 undergraduates. We send a lot of our 6,000 students total. We send a lot of our undergraduates abroad, more than any other school in the United States. A third of all the engineering students that study abroad go to WPI. All right, so what are we looking at? And we need to understand what computer just went blank. What is design? So scientists look at things as they are and ask why. Engineers dream of things that never were and ask why not. And actually, liquid fuel rockets were developed in Worcester by one of our graduates, Robert Goddard, about 100 years ago. But they call it rocket science. I think it's really rocket engineering. Design is important.
Some kind of centenary of his birth or death, or birth recently, right?
Yes. There's some celebration of that. Yeah, thank you. Anyway, design is important. The design methods influence everything we design, and design influences everything we have around us. I'd like to point out that the first canon of engineering ethics, if we had been better at following that, things would go better. Old paramount, the safety, health, and welfare of the public. This should be integrated in all our designs. But all right, design. Philosophy or science? So some people have said that philosophy is what we call thought before it has a chance to solidify into a science. And I would hold that Sue's axioms, which we're going to be looking at in a moment, solidify this philosophy of design into a scientific discipline. So in just an hour, I'm not going to be able to tell you everything I would like to about axiomatic design. And so I would like to provide some motive and beginning with some means, and you'll need to find the opportunity. But there's a link here to all the lectures in my graduate course on axiomatic design of manufacturing processes. So you can access that if you like. Anyway, just another word about science, and I think it's important for what we're seeing going on in the world currently, but particularly in the United States. But the scientific method is terribly important, the most important idea in history for relieving human suffering. And we are now testing to see how we can survive with a leader who rejects science. Okay, so designers dream of things that never were and ask why not. So here, design is important. We should hold paramount the safety, health, and welfare of the public and appreciate that importance as we do design. And then philosophy is what we call disciplines before they solidify into a science. And here is a link so that you can get to my lectures for my online grad class on axiomatic design. And then this notion that when it comes to reducing human suffering, the scientific method may be the most important idea in history. And we are now testing to see how we can survive and function with a leader who denies science. Are they moving along all right now?
Yes.
Yes, wonderful. Okay. So science has a few simple, self-consistent laws, axioms that can be used to solve a wide variety of problems. And so Sue used a scientific method, observations, inductive reasoning, to formulate his two universal design axioms. And so commonality is the basis for scientific laws. I mean, if we look at Newton, the amazing thing was he recognized there is a compact nature to the universe, that things that might seem quite different can actually be associated by fundamental laws. So the motion of the planets and apples falling off a tree can both be explained by the principle of gravity. Nam Su looks at a variety of different kinds of designs, from things that are quite simple to things that are multi-layered and quite complex. And he felt that there should be sort of a compact understanding of what good design was. And that was the beginning of his formulation of principles for design. So again, recognizing commonalities between different sorts of things that have been designed or would be designed. Anyway, so this is the process of crystallization, recognizing commonalities between disparate problems. And I think we have to wonder, since Sue has given us some guidance with the axioms, when we're trying to do design problems, is this trying to like solve mechanics problems without using Newton? All right, so what are these axioms? There's only two, which is nice. Simpler is better if it does the job. So the two axioms, independence and information. So that's the basis of the theory. And then it's accompanied by a design process, which is based on the theory. So it's a formulation of functional requirements representing the design intent, then the physical solutions, or maybe software or organizational, but physical solutions. These are, we call the design parameters, and then a top-down functional physical decomposition. And we'll be looking at those things shortly. Yes, and then the bottom-up integration, physical integration. All right, axiom one, independence. So this provides adjustability and control. We avoid unintended consequences. This often leads to cost overruns and time overruns in design projects. Results in modularity, which I think people understand to be a good idea in design. Basically, so I can adjust one thing without changing others. I can develop one portion of a design without having to change the entire thing. And so as we look for independence, we're able to eliminate some of the perhaps candidate solutions that we might have formulated. So that's axiom 1. Axiom 2, information. Another way of stating it is to maximize the probability of success. So information is the log of 1 over the probability of success. So this relates to like Shannon, Boltzmann. So more information, like more instructions, reduces the probability of success. So we have to think of information as being different from knowledge. Knowledge is good. This helps us understand things and solve problems. But information that is required for a design reduces the probability of success. These are things like tighter tolerances and impossible delays. All right. Axiom 2, since we're really looking at success, and that's sort of overriding, this encompasses axiom 1. It reduces uncertainty, complexity. And once we've applied axiom 1, axiom 2 then ranks the candidates that are remaining that all have independence. And successful design solutions are resilient, which is modularity, resilience, I think are well accepted as good things to have in a design. So I've decomposed axiomatic design into 3 different elements: the axioms, which we just went over, structures, which we'll be looking at next, and the process as well. And so it really goes theory to methods. So we've got 2 axioms, we've got 2 parts to the structure, and we've got 2 parts to the process. For the structure, we've got a horizontal decomposition into domains. So these are different ways, essentially, of describing a design. What do the customers or stakeholders or society need? What functions will satisfy these needs? What are the physical solutions that will fulfill these functional requirements? And then how do we create these things? How do we make them? What are the process variables? So mostly what we're going to be doing is working with these two spaces. And we certainly can get in more into the other ones. We'll be talking a little bit about getting from the customer needs. We're going to leave process variables for another day. Functionalism, this is fundamental to design thinking. And we know this now for many years. Lewis Sullivan, form follows function. So function comes first, then the form. And this was a revolution in architecture. So in axiomatic design, Sue says, all right, we're going to develop the functions first based on the customer needs, and then select the form, the design parameters that fulfill those functions. So Sue mentions bimodal thinking. We need function, physical. Engineers often jump quickly to the physical domain because we're good at it, and we don't spend enough time developing good descriptions of the functions, which would help us get better solutions. So let's take a look at a granular design problem. Let's reduce it down and go, all right, we've just got one element here in the problem, what we would call a single FR problem. We only need one functional requirement that we're going to find a solution to. So first, we need to formulate that so that we satisfy customer, societal needs, stakeholder needs. So satisfy the needs. And we need to do this in a solution-neutral environment so that we don't limit ourselves to one particular kind of physical solution. We would like a large solution space and find the best DPs that way. So the next we will do is we'll generate candidate solutions out of our solution space. These are the things that can fulfill the functional requirement. And so we're working in something that will give us, we're looking for the DPs that are going to best fulfill the functional requirements. We look at constraints, things like regulations or physical laws. Then we say, all right, so how do we select the physical solution that's going to best fulfill this? And we apply Sue's axioms. In this case, where we have only one, the first axiom, only one FR, the first axiom is to maintain the independence of the functional requirements. Since there is only one functional requirement in a one FR design problem, then we just go to, we select based on the information axiom. So we can look at design equations. So in general, the functional requirements are some function of the design parameters. In other words, the design parameters, I adjust some physical element in the design parameter, and I can move the functional requirement so that I get it within a functional tolerance that the customers require. So
this meeting is being recorded and summarized.
So in order to use the design equation, we need functional metrics for the FRs and physical metrics for the DPs. Let's take a look at an example for axiom 2, a 1 FR sort of problem. So we're going to narrow this down to what kind of spring should I have in a clamp. So I've tried to do a rather abstract physical representation of a clamp and showing how that it moves. And we're going to now look at the problem of selecting the spring and exerting the right clamping force. So our FR is to exert a clamping force, and the DP is going to be sort of a spring displacement X. So what kind of spring should we select? We have a design equation where F equals KX, simple linear spring. And we can represent it like this. We put FRs often on the vertical axis, DPs on the horizontal, since the DP is essentially our independent variable now. So as we go to map from the FR onto the DP, we can take a look at two different kinds of springs, K2, a very stiff spring, and K2, a softer spring. So which would be the best? So we have two possible design solutions, and we would need to use axiom 2 to select between them. Which one, K1 or K2, gives us the greatest probability of success? So as we map the FR tolerance onto the DP tolerance, we notice that the stiff spring gives us a smaller tolerance, physical tolerance, than the softer spring. Therefore, the lower stiffness is best. So this allows for variance in manufacturing. When I'm making the cam or the other components, I've got larger tolerances in my design, so I can have more variance in the manufacturing process. As things start to wear, it'll be robust. Temperature changes, it'll be robust with respect to that. It'll accommodate impacts. So we go with a softer spring because it gives us a larger physical space for the design solution. So 1FR design problems. So DPs have a physical entity that is adjusted to get the FRs in functional tolerance. And we're looking for the DP that gives us the highest probability of success. So second axiom, information. Good. We're just looking for the highest probability of success. Now, what happens if we have more than one FR? So we might note these FR 1, 2, 3, and then they would each logically have their DPs. And so DP1 might be chosen for FR1 and DP2 for FR2. However, Nonetheless, DP2 may influence FR1. So as I'm doing something to DP2, perhaps it can have an impact on FR1. So I want to take a look at this kind of representation. So what happens to an FR when I change a DP? And when I'm changing a DP that is not selected for that FR, in other words, their numbers here are different, then I would like the partial derivative of FRI with respect to DPJ to be 0 whenever I does not equal J. So that's how we can maintain the independence of the FRs when we're selecting the DPs. So here's an example. This is sort of a classic, the faucet example. So the question is, I guess, is this a good design? And so, well, we need to decide what does the customer need? So they need to adjust the water so they can wash their hands. And so what do they have? All right, the customer needs deliver water at the desired temperature, desired flow rate. So we can formulate the FRs on that. So adjust the temperature, adjust the flow rate. So we've decomposed FR0 into FR1 and FR2. And now the solution, and this sort of a setup where we've got two valves, we've got a cold water valve and a hot water valve. So question is this a good design according to axiom 1? Well, we can set up a little matrix and see where the non-zero partial derivatives are. So adjust the temperature. Well, I've got the cold water valve. If I change the cold water valve, yes, that will change the temperature. So, but what else happens when I change the cold water valve? That also adjusts. And same with the hot water valve. That will adjust the temperature and the flow rate. All right, so as you can see, we have a full matrix, and so this is fully coupled. So this violates axiom 1. We have not maintained the independence of the functional elements. So these other sorts of handles, which you're probably familiar with, we get the flow rate by moving the handle up and down, and the temperature by moving it side to side. So vertical movement, lateral movement, and then we have now a diagonal matrix, and it is what we call an uncoupled design. So by axiom 1, this is the design that we would choose. It maintains the independence of the functional elements. So the next level of things we could look at would be multi-level design problem, which we sort of looked at before. We have FR0 and DP0. These are the overall solutions. So this is a top-down approach to solving the design problem. So these two get decomposed. So FR0 is going to be decomposed into FRs 1, 2, and 3. And then these each have their physical solutions, DPs 1, 2, and 3. And then this can be further decomposed, and we can keep on decomposing till we get to more and more detail, and the solution to the design problem is obvious. So decomposition. This we need to do. We need to break problems down until the solution becomes obvious, and then integrate the details into a larger, complete solution. So this is reductionism, which is a common thing in science, and we're applying it now to design. So the structure, again, we've got horizontal and vertical. So these are the domains of scope going from customer, functional, physical, process, so why, what, and how. And we decompose the FRs and the DPs into their children. So the children of FR1 or FR 1.1 and 1.2. And there could be more. But we need at least 2, otherwise we're not decomposing anything. So we get down to the leaf level or the nuts and bolts where the solution is obvious. And here we're going from abstract to detail in hierarchies. And here we're looking at domains of scope. So this is what I call the horizontal decomposition, and this is the vertical decomposition. So we've got decomposition rules. Decomposition must be done correctly, as we've sort of implied, so that decompositions need to be collectively exhaustive, so that the children combine, the union of the children should equal the parent. So this is the main decomposition equation. We also need to be sure that the intersections of the children are zero, so that they are mutually exclusive. Otherwise, they will not be independent. I can select FRs badly so that they can't be made independent. And this is what I call CME, collectively exhaustive, mutually exclusive. A thing that will assist doing a CME decomposition is to follow a theme. And sometimes it can be following the energy, sometimes I can decompose temporally, and sometimes I can decompose it in space. So here's an example of a decomposition in space, which engineers should be familiar with. We have a force, and we can decompose it into Fx, Fy, and Fz in a Cartesian space. So collectively exhaustive, mutually exclusive because it's orthogonal, so they're all independent. That's axiom 1. And so when I'm formulating my design problems, I am creating a multidimensional orthogonal space of functions and physical solutions. So the process for doing this, as we've implied, is a zigzagging sort of decomposition. So start. So form follows function. FR0 first, DP0. Then we decompose FR0 in the context of DP0 because FR1 and FR2 are applied to whatever we've selected here for DP0. So if we've decided that this is going to be a pneumatic system, for example, FR1 and FR2 should be applied to pneumatics rather than hydraulics or electromechanics or something. And then for FR1, FR2, we select DP1, DP2, and then so we're zigzagging back and forth doing the decomposition. First the FRs in the context of the upper level DPs, and then the DPs for each of the new FRs. So decomposition rules. FRs are stated in the imperative. They start with verbs. DPs need to fulfill the FRs, and so they start with nouns. We would like the minimum number of FR and DP pairs that are going to satisfy the customer needs. So, and they must be, as I've said, collectively exhaustive. So this is, did we think of everything? And that's sort of an axiom 2 rule. And mutually exclusive with respect to one another. Are they overlapping or redundant? And that's an axiom 1 kind of rule. So when people are having difficulty applying axiomatic design to a design problem, most often I find that the problem comes from the decomposition. So this is the thing to keep in mind. Decompositions seem even. So here's a sort of summary of this and introducing a couple other things. I mentioned constraints briefly. We might have legal regulatory sorts of constraints. We might have societal constraints. Let's be sustainable. And then we can also have selection criteria and optimization criteria. Selection criteria are things that we would like to have in the design, but they don't rise to the level of a functional requirement. So they help me select between DPs, and I might think, oh, I want something that is visually pleasing. While I could make that a functional requirement if I'm a fashion designer, if I'm an engineer, I might just say, all right, this one looks nicer. All right, but optimization criteria, these are things where I need to minimize, maximize, something like that can often be, all right, I need to minimize the weight, and that could be an optimization criteria. Constraints do not take DPs. So these are things that I have to avoid. If I find I need a DP, then it needs an FR. All right, design solutions should be represented actionably. As engineers or designers, we're supplying the design. Here's what the thing has to look like and do. Somebody else has got to make it. Often engineers are involved. Often we need engineers to supervise, but in general, designs are handed over to somebody else. It's interesting when I start working with students, because in the decomposition, we're doing a verbal representation of a design solution. And there's a nice quote by actually a cartoonist from the Midwest of the United States. It says, "Writing is nature's way of letting you know how sloppy your thinking is." And I'm sure anybody that's gone to write down their ideas realizes you've got to stop and think and refine your thinking to render your ideas into words. And same when I go to make a drawing. But for today, we're not considering the drawing part so much, but that can be integrated into, it should be integrated, of course. Many designs require drawings. All right, so mathematics is nature's way of letting you know how sloppy your writing is. So we would, so we're going to introduce quantitative axiomatic design. We'll be talking about that in a moment. So here's an example too of, I like to throw in to show that we can apply axiomatic design to solving all kinds of problems. It doesn't have to be just how do I design a faucet or a clamp. So suppose I want to have a nice vacation and I want to think about it and plan it out. So what would I like? Well, I'd like to be able to relax, and I might like to find some romance. So what would my initial solution be? Well, maybe some wine, some beer, something, or relax, some ethanol, and for the romance, perhaps dancing. So how does this work out? If I look at my design matrix, well, the ethanol, unfortunately, isn't limited in its effects to just the relaxation. And while this is what we call a triangular matrix, so in some situations, we could say, well, whatever the negative effect is of this DP on this FR of the ethanol and the romance, we can compensate for that with the dancing. However, from experience, maybe some of you know, or at least from observation, that no amount of dancing can reverse the effects of excess alcohol on romance. So this is not a good design solution. So what we need to do is look for an alternative DP for the relaxation that does not influence romance, and so yoga. So yoga, we can get the relaxation, and then dancing for the romance. And now we have a diagonal matrix. So this is a preferable solution. So while ethanol is a good solvent, it is not a good solution to problems. It influences too many things. So yoga is independent, think flexibility, adaptability, good design ideas. So maintain the independence of the functional requirements. All right, so let's take a little deeper look at design equations. So the FRs and DPs can be represented as column vectors, and A is a square matrix, ideally. And then we can use linear algebra, and we can adjust things if we need to. So we have a series of equations that I've alluded to before. I'm writing these all as linear equations. They don't need to be. And so we could write this in a compact form here with subscript notation. And often we represent the matrix like this with the DPs across the top, the FRs down the side, and then we have X's and zeros, as we've been using before, to indicate if these coefficients are going to be 0 or non-zero. So anyway, so yes, we talk about the influence. So we put in zeros and x's, and so we can quickly see what's going on. Although here I'm leaving the numbers on so that we can see sort of what's going on. So ideally, we would like to have a diagonal matrix. So then we can adjust the DPs in any order, and this is what we call uncoupled. If we have off-diagonal terms, we can use linear algebra sometimes and arrange it into a triangular matrix. If we can arrange things or achieve somehow a triangular matrix, it is still adjustable without iteration as long as I do keep to this order. So that when I adjust DP1 to get FR1 in tolerance, I may do something undesirable to the rest of the FRs. So I can correct FR2 now with DP2 because it doesn't change FR1. It does change FR2, and again, it may do something I don't want to do to the rest of the FRs. And so on until I get to DP6, which only influences FR6. So I've got one order of adjustment here, but here any order of adjustment would work. Here, if I use different orders of adjustment, I may take an FR out of tolerance that I already got in tolerance, so I have non-productive iterations, and depending upon what my adjustment strategy is, it might not even converge. All right, so fractals, self-similar structure. So we can think of this in design as we're decomposing. And there's things that we would like to have self-similar in design solutions. I've alluded to ethics, for example. And so as we're doing the solution, we can think about decomposing things into many different branches. And when we look at any particular part of the decomposition, it has a similar structure. Often, as engineers, we're given some subpart of this, and we need to create our design solution within the context or constraints supplied by the rest. Anyway, again, reductionism in design. So while I showed that to be very symmetric, the branching can be sort of more natural, like we see in nature, and so that they don't all have to be equal length or all the different branches in our decomposition. So we've talked about decomposition a lot, where we're going from the CNs to the FRs to the DPs, and then creating the design matrix, and then back again, next level down until the solution is obvious. And now we have a fully decomposed details, the FRs and DPs. So here's all the components. Now we need to assemble it into a complete physical assembly. And we can start with sub-assemblies and larger, and then look at the physical integration, because we also need to avoid introducing coupling, because two DPs are interacting that should not be interacting, and because they have been assembled in such a way that they're interacting. So here we're looking for functional independence. Here we're going to look for physical independence to satisfy axiom 1. Also, we need to say, well, which assembly of physical integration will have the greatest probability of success. So again, as we're going through the physical integration, we need to keep applying the axioms. Okay, so creativity. So we would like large solution spaces for looking for candidate DPs. So we need to promote multiple alternative DPs. So this increases our chance of finding the best DP, and also is important for making stronger patents, because when you write a patent, you can have a list of claims. You have to disclose what you think is the best, but it's nice to claim other things to give your patent sort of broader coverage, so it makes it harder for other people to get around it. So anyway, to create a large solution space, the FRs need to be solution neutral. They should not suggest a physical solution. And then we need to see if we can formulate the FR so that it is closer to the DP and away from potential DPs. closer to the CN rather, and away from the potential DPs. So one of the questions is, what does the customer really want? It's important to listen to the voice of the customer, but you don't want to have the customer dictate the solution because their vision may not be so broad. So people have credited Henry Ford with saying, if I'd asked people what they wanted, they would have said faster horses. Of course, if he had decided to just listen to the voice of the customer, he would be an unknown horse breeder from Michigan. So we need to abandon horses as the definition of transportation, which is difficult if all you've seen is horses. And so if you're just looking at horses, your solution space is too small. So who is the customer and how do they define value fundamentally? So recognizing it's a transportation problem, not an animal breeding problem. So formulate FRs and constraints. Fundamental needs of stated CN should be understood, appropriately formulated into FRs. So one of the things we can borrow here from Lean is, and the Toyota production methods, ask why 5 times to get to the root of the problem is what we learned from Toyota when there is a problem. So we're trying to solve a problem. Let's ask why several times when we start formulating our FRs and see if we can develop a better FR that will be more useful in finding a solution. So understand, why do you want faster horses? So if you can't think of several FRs that can satisfy, several DPs that can satisfy an FR, then maybe that FR is worded so that it is too close to the solution, the DP. So what we need to do is formulate the FR so we leave a large physical solution space, as I stated. So critically evaluate the FRs. The solution is not going to be better than the functional requirements. That's what you're set out. Those are the design intents. So here's a little illustration, sort of. Let's get more blue sky for candidate DPs. Let's move the FR and not get it too close to the solution we're looking for, but get it closer to the customer. All right, here's another point, and it's particularly important now. It's continually important because all kinds of technological changes and new abilities are appearing. So new production technologies, but all kinds of other things. The artificial intelligence can get us solutions that we didn't think would be achievable before. So as we get new knowledge, we need to re-examine our FRs. And so here's an example. For transportation across New York State, the Erie Canal traverses New York State, gets through the Appalachian Mountains, upstate New York. And it's really this connection that gets a connection from the Atlantic to the Great Lakes on the other side of Niagara Falls. So this connects essentially the Hudson River, which is really an estuary and like almost a fjord. And that connects that to Lake Erie and now access to the interior of North America from the Atlantic Ocean. And this is what makes New York eventually to be a kind of one of the world capitals, the Erie Canal. However, the Erie Canal goes in 1825, and steam engines come in and trains, and then through the same gap in the Appalachian chain in upstate New York, they laid rails, and then you had railroad. So a new solution. So formulate the FR as a solution neutral environment, dream in color, and and watch and see what are the new advances that could be used. So CK theory comes out of the École de Mines in Paris, and I think it's very valuable to apply it as we're looking at solutions because we can have some nice concepts. This would be great. Do we have the knowledge to do that, to actually implement these new concepts? So when I'm teaching this, I like to say, all right, you could have a good idea. Don't give up on it. Think about what knowledge do we need to develop. And often in axiomatic design, too, sometimes we're going, well, what are the probabilities of success? Or how does this DP actually adjust this FR? But so we can go from concepts to knowledge, and then we can sort of decompose these and find other connections and so forth. So there's a whole body of literature on the CK design, design theory. All right, just to start summing things up a bit, decomposition is a key. So we need to be able to decompose the problems appropriately and then integrate them. Metrics are important. If you cannot measure it, you cannot improve it. And often we get going in axiomatic design and we have these nice verbal descriptions, and then getting the metrics can be difficult. We need to do that. I like to know when my plane's on the takeoff roll that they used metrics for designing the plane. So they're important. We can do better creativity and innovation, greater success in providing value. We need to know how the DPs are influencing the FRs. We need to be able to verify that our decompositions are collectively exhaustive and mutually exclusive. And an interesting one is, how do I measure design progress? So sit in a design review sometime, maybe just as an observer, and say, how can I tell if they're making progress in this design review? Have they advanced the design in such a way that it's more valuable than it was when they started? So the decomposition is quite helpful for this because we're breaking it down into small problems. Sometimes a different decomposition might work better. And we see, all right, are we making progress in solving all of these little problems that add up to the big design solution? Okay, we had a couple kinds of equations just as review. So we've got the decomposition equation. So the children need to combine to equal their parents. They're orthogonal, so we're probably looking at a vector addition problem. The design equations, how do the DPs influence the FRs? So we need functional metrics for the FRs, physical metrics for the DPs. We use this to check on axiom 1, make sure they're independent. And then we need to know probabilities of success for ranking the remaining solutions after we've checked for independence. And so that's the log of 1 over the probability of success. So we can see, we've got sort of top-down design decomposition equations. Then horizontally, we're looking at the design equations. So it's sort of like piecing together a puzzle. And if we include sort of concept knowledge, we can think about adding other dimensions as well. So systematically, include creativity in axiomatic design, integrate sustainability into the process, make AD part of innovation of Green New Deals. I need to put up some of our politicians that we could be more proud of in the United States who are pushing for better societies. All right, concluding remarks. Find creativity in the details. Go for the larger design space. Record the options, the equations, selection, so that you have this as knowledge management. So you accumulate knowledge when you're doing design, and you have all the little pieces, the little problems that you solve. Maybe you put them together in a different way, or you learn from those. But so axiomatic design, the way it's structured, lends itself to creating knowledge for design and solving future design problems. hold paramount, safety, health, and welfare of the public. That needs to be integrated into all engineering work so we can foster a green innovation revolution. And it's for the benefit of everyone, everywhere. So we have had good presidents in the United States. References, there's 4 books out on complexity, on axiomatic design. I recommend them all. And first 3 are by Nam Su. This Principles of Design, I think, is a classic. And this one is can be very good for teaching from. It's got a lot of contributors and a nice team of editors. So let's see. We've got coming up the International Conference on Axiomatic Design here at MIT, or as we call it, the WPI of Eastern Massachusetts. And so that will be in June. Final paper submission actually is pushed back to this Saturday. I think you can still get an abstract in. But anyway, so there's this is the 17th in the long series we've had on axiomatic design, and coming back to MIT where it started from. End products of design: functional, actionable, realizable. The societal needs have taken a back seat largely in the United States, unfortunately, to stockholder value. This really starts under Reagan administration with all the deregulation, including deregulation of essentially the truth in broadcasting, as cable can come in and unregulated broadcasting of advocating political decisions or political positions. Anyway, we have to practice ethical engineering. If it's not ethical, it's not engineering, it's destructive technology. So the ethics has to be in all branches, all solutions. Thank you very much for your kind attention.
Thank you, Chris. I think Sham has a question. Is axiomatic design a way of understanding the design process or of making better designs?
Both. So what we have is a
You
framework.
can stop sharing your screen if you choose. Yeah.
Okay.
It's a kind of higher level philosophical theory level question. Is it a tool for making better designs, or is it a way of understanding how the design process works?
Well, this is not really a choice. It can do both. Those are not mutually exclusive choices. So yes, we use it for creating design, and yes, we can use it for understanding how the design process works.
So in using it for making better designs, one of the critical steps that you mentioned is decomposition into collectively exhaustive and mutually independent parts, which is very difficult to do in any real problem, because components of a problem, decomposing a problem into parts which fulfill these two conditions is not easy.
I agree, sometimes it's not easy, but I don't see another way of doing this. And we use the decomposition on all kinds of things. We don't do a good job teaching it. I think if we did a better job teaching it, more people would be able to do it. So spending some time trying to figure out how to facilitate the decomposition. And as I said, this is, you're right to identify that as a challenging aspect of this. I've been teaching graduate courses on axiomatic design since 1990, and gradually introduced it to the undergraduates, and think that actually we should be, and actually have introduced it into high schools, and with pre-college students. It can be done. And as I said, this is often where people have the most trouble, is with the decomposition. So you're right to recognize that as a challenging part.
There is another question. It says, in domains like RF engineering, where parameter coupling is unavoidable, how would you interpret or adapt the independence axiom? I think it follows Shyam's question in a way. Yeah.
Yes, well, and there are some things that are not going to be decoupled in an ordinary sort of way. So I've worked with metallurgy. So we know that as we try to make steel harder, it also gets more brittle. So what we need to do is and what is commonly done, and I think everybody understands the solution, is we case harden something so that we're able to have a hard surface where we need the surface hard and a soft interior so that we can reduce wear and avoid brittle fracture. So I don't know the field that well that you're discussing, and there are some things where we just recognize that, yes, there is coupling, and this is going to be an issue, and we need to somehow deal with this and the way we're adjusting things or compensate for it. I'd be glad, perhaps at another time, to take a detailed look at some particular aspect of that and try to give you a better answer about how it could be done.
Sunil?
I have one question now. Since you mentioned about CK theory, so when we actually take the axiomatic approach, you are essentially looking at modularity in the solution. But according to CK theory, it is the non-modular structures which actually create possibilities for generativity. So how does this? So does an axiomatic design lead to a lock-in is my question.
No, I'd like to discuss it with you in more detail at some point. And how the CK can be integrated with the axiomatic design without running into an apparent contradiction that I need to have some sort of interactions. One way of addressing this is to have FRs that are addressing the interaction. For example, one person that I was working with doing business design said, all right, I want to take two separate medical facilities, one that's, say, doing orthopedic work and another that's doing, I don't know, something else, cardiac work, and I want to integrate them into one unit. And he said there should be some savings there because there's things that overlap. But he says, but if I strictly say, all right, I need all of these things independent, then I'm not seeing the synergy that I should get from the integration. So it might be a similar thing to what you're talking about. So I said, well, what you need to do if you're looking for synergy and you're trying to do that, you should have an FR that addresses the synergy issue. And so if there is a benefit between collaborating, the potential benefit that you're trying to realize between some sort of integration, collaboration, overlap, I would suggest seeing if that can be its own FR, and then you have some sort of integration strategy that is going to help realize that FR.
So this is where, like, for example, given today's context of AI, in framing these functional requirements, can there be a more creative role of AI? which can deal with the kind of point which you're making?
Yeah, that's a good question, and I've been trying to see what it can do. So the AI, as I've been able to use it, is good at finding what everybody else has done and seeing what other word combinations have been used. And so it does help say, oh, geez, I hadn't really thought of that. It's good at coming up with, I would say, known things, or it's working on word combinations. But as I use it to try to say, all right, well, let's apply axiom 1, it's not able to do that. So I'm interested to see where it can go, and I'm thinking people are working on it to make it more creative, but to be able to train it to follow axioms. But so far, I found it useful for coming up with suggestions. But usually, this idea of minimum number of FRs, it's coming up with so many, and you keep trying to prompt it to say, all right, well, let's have fewer. What are the most important ones? What are the most important ones? It might be possible to train it to do that. When I give it the faucet problem, it's got a long list of functional requirements.
Thank you.
Yeah, it's something we need to keep trying. And AI, as they say, the worst AI program you'll ever use is the one you're using today.
I think it's an interesting discussion on CK and FR, and the point that came to my mind was when you have less modular, more composed knowledge, you may have to find some other way to get around it through an intermediate function, such as what I think Chris suggested, functional requirement. So in a way, AI is not able to possibly identify a integration and find a gap in which it can fill a solution. So I think in that sense, you take CK and axiomatic design, what you are able to do, I would say, is to go back and forth between, do I have the knowledge to do this? Do I have this? If I do this, can I do a particular task? Or can I separate the knowledge, information somehow through some kind of a boundary structure? So we could open up all kinds of questions as I see it, but that's a long discussion.
It would be a good discussion, and I think it's something we need to keep trying. I mean, I've been telling my students for the rest of our careers, we are all going to be seeing what AI can do now. And we need to actually find things we can do to add value beyond what AI can do.
So are there any other questions?
I think there's
Great
one
discussion.
question in chat from Aditya Kaushal.
I think I took that question. Another one? Second one? No. He took that question, yeah, on the RF one. Is there anybody else who wants to say something from an education point of view or from practice point of view? Please go ahead and speak. Otherwise, we will close the session.
Just one point. The ICAD coming up at MIT. I hope they're going to. I hope they're going to Zoom it so that people can participate remotely. Because
can you send a link once it is done, so we will distribute?
Yeah, I mean, I can send you. Why don't I send all of my slides someplace?
Yeah, please
send me an email. Yeah, send me an email, then you'll have all of that. But it is AI is one of the main theme beyond the axiomatic design of the conference. So that could be very interesting. Boston at best is expensive, and traveling to the United States now is a little crazy.
Yeah, if you are going to Zoom it, tell us. We will share it with the people who, the group of people who generally attend these lectures. Yep.
Yeah, I'll put it as a PDF or something so it's smaller and send it to you.
Yeah, I'll send an email reminding you also.
Oh, great!
Thank you very much. Thank you very much, Chris, for a really a wonderful lecture, and maybe at some other point in time you can come back and actually pick specific like sports equipment and other things as a way to illustrate axiomatic design in more detail. That would be wonderful.
I'd like to do that sometime. Thanks.
Okay. Thank you. And
yeah, thanks for all the nice questions.
We will distribute this slide.
Thank you.
Yeah. Thanks for the good discussion. Nice questions.
Thank you, Mr. Chris.
Thank you. Bye.